All right. So in this last video of this topic, I will try to show you an extension to essentially other functions, which I'm going to consider a polynomial function. In fact, the example will be a quadratic function, and we will also extend it to n data points. Okay, so let's put the example down. Example. So extension to fitting polynomial functions and with n data points. So we are extending both the function to a quadratic function as an example, and I'm going to keep this time n data points rather than 3 or 4 data points. Okay, so let us consider this is going to be a bit a lot of small computations, but the concept basically is exactly the same as what we have done before. Okay, because of keeping n data points, we will have a lot of summations in terms of n data points, but please bear with me for this example. Okay, consider the data set. So our data set this time is composed of ti and f of ti's, and f of ti is equal to, let's say, fi's. So I have pairs of ti fi data points, and how many of them? We have n of them. Okay, now let's say that we have f approximate function f cap of t is equal to alpha 1 t squared plus alpha 2 t plus alpha 3. Okay, so since this is a quadratic function rather than a line, now we have 3 unknowns, right, with alpha 1, alpha 2, alpha 3 unknown parameters. Okay, what is our error? Again, define the error as essentially e at time t is defined as f of t minus f cap of t. F of t is coming from the data, f cap of t is coming from the parametric function for the given t. Okay, so similarly, e square of t becomes simply f of t minus f cap of t squared. Okay, now total mean square error, total mean squared error, or you can call it total or mean squared error. It's the same thing because mean is nothing but a summation. Okay, so basically we have I from 1 to n e square at ti. Okay, now what is that? Let's expand this. So I have I equals 1 to n. I have f at ti minus f cap at ti squared. Okay, and what is that equal to? I know what's the parametric form of f cap. I equals 1 to n, right? F at ti minus, now f cap is given in this functional form, so it's going to be alpha 1 ti squared minus alpha 2 ti minus alpha 3 squared. Okay, so we have e of alpha 1, alpha 2, alpha 3. which is also equal to j of alpha 1, alpha 2, alpha 3. Okay, so our objective function is nothing but the mean squared error function, which is given by this summation. Okay, so now the necessary conditions, you see I'm following exactly the same approach. So what I need is 3 different derivatives with respect to each alpha I. Okay, so dE over d alpha 1, okay, of this function. So summation over here, I equals 1 to n. Now 2 times the entire expression, f of ti minus alpha 1 ti squared minus alpha 2 ti minus alpha 3, and a derivative with respect to alpha 1. Okay, so alpha 1 is over here, no other alpha 1 term. So I have minus ti squared over here with the derivative with respect to ti. The derivative with respect to alpha 1. Okay, so let's make the multiplication to try to simplify things a bit. So I equals 1 to n, right? So minus 2 ti squared, f of t1 is actually equal to f1. Okay, so f at ti, right? So this is not t1, f of ti, so this is fi. Let's shortcut that for fi. Okay, and plus, right, 2 alpha 1 ti to the power 4 plus 2 alpha 2 ti to the power 3, alpha 2 ti to the power 3 plus 2 again alpha 3 ti to the power 2. Okay, I hope I don't have any mistakes here. All right, so that is equal to 0. Okay, in fact, so that means I can actually could have canceled all the 2's because we are equating that to 0. Okay, now let me take the summation to the inside. Remember, what I'm trying to do is I am trying to find an equation in terms of alpha 1, alpha 2, and alpha 3, and possibly a term on the right hand side. So what I'm trying to do is find the coefficients of alpha 1, alpha 2, and alpha 3. So if I try to do that, let's try to find out what's going to be the coefficient of alpha 1. Okay, so you see alpha 1 is here. There is ti to the power 4, and you have the summation. So you have summation I equals 1 to n, right? Ti to the power 4 times alpha 1. So ti to the power 4, the summation, and alpha 1 is over here. Plus, again, the summation I equals 1 to n. Okay, similarly, alpha 2 is here. Ti to the power 3 times alpha 3 plus, again, summation I equals 1 to n, alpha 3 ti squared times, this was alpha 2, sorry about that. Right, there is a correction here. This is alpha 3, and that's going to be equal to, there is also a term here without any alphas in it, right? So that's going to be equal to, again, summation I equals 1 to n, and you have ti squared fi. Okay, so ti squared fi. Okay, so that's the term on the right hand side. So I'm squeezed over to the right, but sorry about that. So that is one of the equations, right? Okay, so that's our first equation. So each partial derivative with respect to each alpha essentially gives us one equation. You see, a term times alpha 1 plus another term times alpha 2 plus another term times alpha 3 is equal to a constant here. Similarly, let's also quickly do this for the other derivatives. So I'm gonna try to take those derivatives as well. So dE over d alpha 2, so that's going to be equal to I equals 1 to n. So I'm going to quickly fill that out for you. So that's going to be 2 times fi minus, again, alpha 1 ti squared minus alpha 2 ti minus alpha 3 times inside with respect to alpha 2 minus ti, that is equal to 0. So that's going to allow us to cancel the 2 over here. So that's going to be, again, summation, expand the inside, e equals 1 to n. I have minus fi ti plus alpha 1 ti cube plus alpha 2 ti squared plus alpha 3 ti, and that is equal to 0. Okay, and this gives us again the equation. If I regroup, expand, put the summation inside of the parentheses, so I have I equals 1 to n ti cube times alpha 1 plus I equals 1 to n ti squared times alpha 2 plus I equals 1 to n ti times alpha 3, and that is equal to summation I equals 1 to n ti fi. Okay, so that is yet another equation. Okay, finally dE over d alpha 3, and I'm going to put this again directly in. Okay, let me also for completeness write this down for you. I equals 1 to n, again 2 times fi minus alpha 1 ti squared minus alpha 2 ti minus alpha 3 squared, sorry, not squared, because that's the derivative. So I have minus 1 with derivative with respect to alpha 3, that is equal to 0. Cancel the 2, and you get, after you distribute everything, you get the final equation. Okay, I equals 1 to n ti squared alpha 1 plus I equals 1 to n ti alpha 2 plus I equals 1 to n. Basically you have 1 over here times alpha 3, and that is equal to summation I equals 1 to n fi, which is your final. So this was your second equation, and that is the last equation. Okay, you see that there is a structure here, in fact a very nice structure, right? ti to the power 4 3 2 t square fi 3 2 1 t to the power 1 fi and 2 1 0 fi. Okay, so there is decreasing powers of ti. So if I put this in a matrix form, it's gonna look actually in a very nice structure. So finally put into matrix form. So it's a 3 by 3 matrix, although it's going to be quite a large one. I have alpha 1, alpha 2, alpha 3, and equals to another over there. Let's change the color for the coefficients. So I will have here summation I equals 1 to n ti to the power 4, right? I equals 1 to n ti cube, I equals 1 to n ti squared, and that is equal to, on the right hand side, I is equal to 1 to n ti square fi, right? And you have I equals 1 to n ti to the power 3, I equals 1 to n ti square equals 1 to n ti. On the right hand side, I equals 1 to n ti fi, and finally I equals 1 to n ti square 1 to n ti, and I equals 1 to n times 1, right? Actually summation of 1. On the right hand side you also have no ti's remaining. I equals 1 to n fi. Okay, you see that this matrix has a special form, right? It's basically a symmetric matrix, right? You see that these terms are exactly the same. Okay, so it's a special form. And note, as we have done for the previous example, same result can be obtained by using simply A transpose A alpha equals A transpose B. Okay, if you write the A and B matrices in terms of the given n data points. Okay, all right, so that concludes our discussion. So this is why this method is called the method of least squares, because you can see that everything basically is based on defining the squared error and actually finding the minimum of that. Okay, so you sum the errors over all data points and you try to find the minimum of that total or mean squared error. That is why our this topic is called the method of least squares. Okay, and it's used everywhere, from training neural networks to fitting functions to fitting transfer functions to data and so on. Okay, now, so this the reason that we have covered this is that this is also related with another concept. Okay, so this is this let's say topic is called optimization theory. Okay, there is something called what is optimization theory? It's about essentially minimize or maximize a function of multiple independent variables, multiple but finite independent variables, right? We have, let's say, alpha 1 up to alpha n, that we have tried to minimize or maximize with respect to. There is another topic which is tightly related with this, is called the optimal control theory. Optimal control theory. Okay? What is optimal control theory? It's again minimize or maximize a function, but this time of other functions. We can call them other independent functions. Okay, so what is the difference? The difference in the optimization theory is that you have a function of a number of parameters. Parameters are just numbers, okay, that you are trying to find. In the optimal control theory, you are trying to minimize or maximize a function, but the function is not of a function of a number of parameters, but it's a function of another function. Okay, now this is getting kind of twisted, but if you think about control theory, okay, designing a controller is something like that. Okay, basically, for example, in control theory, you're given basically a system, right, G of S, which has an input U of t and is an output Y of t. What are you asking? You are asking, can I find a U that's going to give me the desired Y? Okay, so find U of t to lead to desired Y of t. Okay. Now, how do you combine optimization with control theory? Well, you can ask this kind of a question. Can I find an objective function? Okay, so optimal control. Basically, can I define an objective function, which is J, but J will be a function of U to minimize, maximize. Okay, and find the optimal U star of t. Okay, so in optimal control theory, you are trying to find an optimal control input that's going to drive the plant to the desired response. Okay, so the reason we covered optimization or an introduction to optimization is that that's going to lead us to the so-called linear quadratic regulator in the coming weeks. Quadratic regulator, which will precisely do that. What it's going to do is that define an objective function, which will be a function of the input as well as some other things, and it's going to have a meaning, and minimizing that function basically will lead us to find an optimal control, U star, in order to drive the plant to the desired response. Okay, and in order to do that, we will basically use concepts of optimization and concepts of optimal control theory. But these are very introductory, and we are gonna some things will be kind of a bit obscure, maybe at times. But remember, these are all covered in 2 graduate courses in our department. One is the optimization course, which covers this part of where you have finite number of variables or parameters, and in the optimal control theory where you have independent functions that you are trying to find. One good thing about optimal control theory is that it's quite hard, but it can be approximated as an optimization problem. Okay? If you have further questions, we can discuss them during our time. But this is basically the reason of covering this topic, is to give you a background in trying to understand the linear quadratic regulator, which is a very prominent, very powerful optimal controller that you can come across, and you will use that in your laboratories to design state-of-the-art controllers for especially the nonlinear pendulum model. Okay, so that's going to be all for now, and see you guys on our lecture time.